Welcome to the jungle. Thank you for joining. Once again, I'm your host, Gringo Curt. If you've seen previous episodes, then you know that we've got a lot of history to learn, so I'll keep this intro short. This is the timeline. This is when the Earth and the Moon were formed. And this is where we left off. So, let's get into it. Now, with the Theia situation, broadly described, it's time to explain some related differentiation concepts. From a perspective, differentiation periods can more broadly be described like this. They are the events that cause space clumps to become planet-shaped. You see, there's no edge to liquid mass, and when liquid mass is spinning, the heaviest elements tend to sink, while the lightest elements tend to rise. To get a clear understanding of why, here's a simple experiment. Try to spin a lopsided basketball on your finger. If the ball is truly lopsided, then it'll be impossible, even for these guys. Now, when a hypothetical space clump has melted into its liquid spherical form, all of the heaviest bits that it had previously accreted naturally sink to its center, because this causes what was a lopsided wobbly spin of an awkwardly shaped space clump to become the efficiently smooth orbital spin of a rounded, centrally weighted planet. And that brings us to the unnamed moon of Earth. It's easy to recognize that it went through a differentiation period because it's, well, round. However, its weight is lopsided, so it doesn't spin. During our moon's differentiation period, a considerable amount of Earth's attraction was influencing where the moon's heaviest elements inevitably settled into place. For this reason, the face of our nameless moon will forever be more attracted to Earth than its backside will. Back in the day, our newly forming atmosphere gradually began capturing the water vapor which previously was being lost to space. After the accumulated water vapor condensed, it hypothetically would have become the foundational depths of Earth's oceans. The friction of Earth's iron and nickel core against its less dense outer layers caused it to become a low-powered electromagnet. The electromagnetic energy created formed into Earth's electromagnetic bubble. This force field protects us by deflecting a significant amount of solar radiation away from Earth. Here's another interesting note. While encircling the Milky Way galaxy, our sun creates a wake. To get a more earthly perspective, let's look at a whirlpool. The sun is riding cosmic waves while spiraling around the Milky Way galaxy. Meanwhile, the Earth is caught within our sun's cosmic wake. Scholars hypothesize that after Theia's violent merging with Earth, its surface layers went through a cooling period that lasted approximately 600 million years. Throughout this period, the releases of volcanic outgassing became a large contributing factor towards furthering the formation of Earth's early atmosphere, which, during this portion of Earth's timeline, primarily consisted of water vapor, carbon dioxide, and nitrogen. While the unnamed moon was taking shape, the Earth's crust was cooling down, and oceans were accumulating above it, let's now readjust our focus back towards space and another solar system event that was hypothetically about to occur. In this event, both Jupiter and Saturn find themselves drawn to the center stage. By this point, they had formed into the solar system's largest planets, and they both orbited our sun from much greater distance than the likes of Earth. This is because they were accreted from lighter materials that existed from further away. Known as gas giants, they're proof, given enough time, even light stuff can eventually accrete into massive objects. Okay, so here's where astronomers need to do some detective work. Current evidence suggests that the orbits of Jupiter and Saturn migrated closer towards the Sun. Present models suggest that Jupiter's orbit eventually moved inward so close that it eventually orbited the Sun from as comparably close as Mars does today. From there, both the planets' orbits stopped shrinking and started regrowing. As this happened, both planets logically cooled down while migrating into more expansive zones of slower-moving orbitals. Ever since, Jupiter and Saturn seem to have found an equilibrium, based on their relative sizes, temperatures, and orientations to their other neighboring solar bodies. So, while these two orbiting gas giants were hypothetically migrating toward the Sun, one of 4 scenarios could have happened to the planets of our inner solar system. Some protoplanets could have been absorbed by direct contact with Jupiter or Saturn. Some could have been gravitationally slingshotted completely out of our solar system, causing them to become starless, free-floating planets. Others could have been destroyed by the impacts of all the rocky materials that the gas giants were slingshotting around in various directions. And finally, some may have been impacted but not destroyed. Evidence of the 4th scenario, the impacted but not destroyed scenario, is revealed when studying craters. Evidence shows us that many craters were formed by protoplanets, aka planetesimals, that smashed into the rocky surfaces of Mercury, Venus, Earth, and Mars during this period. The backside of Earth's unnamed moon also took a beating. It's those craters that reveal the strongest evidence for why astronomers think that the great impact of Theia occurred before the dramatic orbital movements of Jupiter and Saturn. On top of crater analysis, it's notable that the asteroid belt also seems to have been affected. There, astronomers have discovered traces of chemicals that bind tightly to iron on asteroid surfaces rather than beneath them, which is what would more naturally be expected. Some would even say that our solar system's inner asteroid belt may not exist if this event never occurred. Due to weathering, and because of plate tectonics, the surface of the Earth has since been renewed. And because of that, it possesses relatively few scars from the happenings of these distant events. So, most clues have been discovered when scholars have focused their astronomical studies on the aforementioned neighboring planets, along with the backside of our moon. Astronomers have used various crater counting methods to estimate the ages of these scarred worlds, and also to estimate the time frames for which the material slamming into their surfaces occurred. The event also seems to lead into the next hypothesis that scholars have dubbed the Late Heavy Bombardment, or LHB for short. This hypothesis is pretty cut and dry. Basically, Earth was heavily bombarded by comets and asteroids during this period. Pretty simple. One interesting line of recent research indicates that the number of impacts during the Late Heavy Bombardment drastically increased approximately 3.8 to 3.9 billion years ago. It seems evident that asteroids and meteorites initiated the LHB event, but then there was a significant uptick in activity, and it appears evident that it was the type of activity that likely would have occurred during the previously described movements of Jupiter and Saturn. But we don't entirely need to look toward the sky for supporting evidence. Although the majority of Earth's scars have long since been tectonically covered or weathered away, researchers are still able to study millimeter to centimeter thick layers of rock droplets known as spherules. Brandon Johnson of Purdue University said, "Spherel layers, if preserved in the geological record, provide information about the impact event when the source crater cannot be found." Johnson led a study that used models to deduce impact sizes based on the properties of spherel beds. His co-author, Jay Melso, also at Purdue University, claimed that the spherel beds studied suggest that some asteroids were about 40 kilometers in diameter. For perspective, that's drastically larger than the Chicxulub asteroid, which is famous for killing off non-avian dinosaurs roughly 66 million years ago. By comparison, that asteroid was about 12 to 15 kilometers across. Within the NICE model, which is a theory named after a city in France, astronomers claim that the migration of Jupiter and Saturn inward also destabilized the orbits of Uranus and Neptune. It states that the lessening of the gravitational pull from the gas giants caused the solar system's 2 ice giants to respond more with each other, causing them to ultimately switch orbital positions. They switched back again, but this rare occurrence hypothetically would have gravitationally kicked some of the icy material that had been accreting near them. Some of the icy planetesimals were slingshotted outward towards Pluto, partially explaining the formation of the Kuiper Belt, while other trajectories sent icy planetesimals traveling toward our solar center. Some of these icy materials possibly impacted Earth. Its newly developing atmosphere had become relevant enough to trap the water that would have vaporized upon such impacts. As the water vapor condensed, it would have increased the depths of our planet's newly forming oceans. Looking back to the timeline, from roughly 3.8 billion years ago and onward, our solar system can most simply be described like this. Earth orbits the Sun, and its axial tilt is the reason for the seasons. Earth is a relatively close neighbor to 3 other planets. All 4 of these rocky planets are spiraling along the orbital plane of our inner planetary system. Zooming outward, past our inner asteroid belt, we reach the solar system's outer orbital disk, which includes our 2 gas giant planets and our 2 ice giant planets. Beyond them are some Pluto-sized orbitals mixed among the orbiting asteroids of the Kuiper Belt. A bit further than that, and we're reaching beyond the heliosphere. Scientists estimate that the edge of our solar system is about 15 billion kilometers from the Sun. Everything contained within our heliosphere surfs the waves in a semi-elliptical orbital pattern around the center of our Milky Way galaxy. And now, the stage has been set.